Now, at that max transfer point, we can draw a free body diagram to see the forces that will be transferred into the wall, which will be the entirety of the horizontal forces minus the sliding resistance of the anchor, which will be the overburden weight multiplied by coefficient of friction. This is what we call RS prime. And then, before moving into the code, we'll define our two situations in which the walls experience load. So we have our RS prime. That's going to be the horizontal forces on the anchor minus the sliding resistance that we're going to use the overburden force times the coefficient of friction. And don't mistake this with the friction across the saddle, but this is sliding friction between soil and concrete. The same sliding friction coefficient we're using when we're doing our sliding force checks. So condition 1 is pre-fill. We have, before fill, we have dead load only, right? This is just the weight of the cables and the decking when we hoist our cables. We can't rely on any of the ramp fill in between the walls to distribute the load. So in this case, we divide the adjusted horizontal force, RS prime, equally into each wall. And remember to use dead load geometry and dead load forces only, or else your checks definitely will not pass. And that just gives us our P wall value of RS prime over 2. Our other situation is going to be our post fill. So our total load condition, and after filling the ramp and finishing the abutment, this is not as simple as just distributing the force based on area, the ramp wall area versus ramp fill, because the materials are stiff and have different stiffnesses. Stiffness is a measure of resisting deflection when force is applied. So stiffer structural elements will take a larger portion of the loading, and usually the loading is distributed based on a measured stiffness. And then due to a variety of unknowns like workmanship and air voids, we can't determine the stiffness of each material exactly, so we'll turn to the density as a proxy. If the fill density is 1900 kilograms per meter cubed and the wall density is 2100, the wall stiffness portion would then be 2100 over 4000, and the wall would experience about 52.5% of the load. While the approximate densities aren't perfect matches to solve our problem, they can help us validate and develop our engineering judgment for this. Given the variability and the unknowns, we'll conservatively assume 60% of the total load is distributed to the walls. This is opposed to about 20 to 40% if we were go off this based on area. So we have our P wall value of 0.6 R prime and then divided by 2, so as to distribute the force into each wall.